We'll have a brief introduction to the main ideas on how the northward propagation MISOs are generated and maintained. So there is the propagation part, and then there is the genesis part. The ideas range over these hypotheses, you can say. External forcing of the MISO, we will see where that could come from. Circumnavigating upper tropospheric ISO. So we had talked about this idea of circumnavigation in the case of MJOs, where we said they cross the maritime continent somehow into the West Pacific, and then convection dies off because there is cold SSTs in the eastern Pacific. Then they cross over the Atlantic onto Africa and back into the Western Indian Ocean, where they are fired up again. But the problem there was that the MJO decorrelation scale is much smaller than the scale of the circumnavigation. So the idea is not that solid, even though there is always evidences you can find of in various non or dynamic variables in terms of MJOs going across. The idea of circumnavigation of MISOs is that the MJO phase is somehow associated with the genesis of MISO, and so you can imagine that this idea would say there is genesis of MISO, let's say in the Western Indian Ocean, which is related to the previous phase of MJO, and then as it enters the central Eastern Indian Ocean, it's somehow steered northward instead of continuing eastward. Again, this idea is not completely robust and doesn't seem to be working all the time anyways. Influence of large-scale external forcing such as Enso and the Indian Ocean Dipole. There are many studies which have looked for these kinds of relations. There is some positive correlation of Enso with the MISOs at the beginning of the season, but doesn't seem to have much of a robust correlation through the season. And the studies by Harry Hendon and others argue that MISOs are like MJOs, essentially internal variability of the atmosphere, which means they are just generated by the nonlinearities, which you think would make them very difficult to predict. But as we saw in the composites, once they are initiated, they may have a systematic evolution which could still make them predictable at some time scale with some lead time. IOD happens in September, October, November, and doesn't have a very strong signature in the monsoon season, so that relation is not very robust either. The other idea is relation with extratropical variability. We'll see one specific feature, the mascarene high, which is associated with the monsoon in some ways as it pumps up and down. Where it is located and how that would affect MISOs can be seen this way. So in the active monsoon season, the mascarene high that's sitting here can actually create these outflows when it pumps up and down, which can affect the moisture supply onto the Bay of Bengal and the Indian subcontinent, which would provide moisture flux across South Asia. So this is the trade wind surge MISO theory, and there is some evidence that the moisture that's coming in here, maybe up to 70%, is picked up in these trade wind regions, and the rest of it is picked up here over the upper Indian Ocean, Arabian Sea, Bay of Bengal, and so on. Some of it curves back, goes across, curves back onto the subcontinent. So there is that idea. Of course, you have to still explain the thing we talked about before, the cross-equatorial gradient, the lateral outflow from the desert, and the lack of inertial instability. But the ideas that talk about the break period role for the strong PV flux out of the mascarene high argue that there is a cross-equatorial PV flux which interacts with the outflow and basically avoids the Indian subcontinent and robs the moisture that is supposed to go here, so maybe contributing to the deficient rainfall and break periods, which can be interpreted as occurring at meso timescale and related to meso. So the active and break periods are obviously meso timescales. So these are two ideas. The other one is more of like a self-induction or the processes that we talked in terms of in the case of MJOs, where the waves set off in the dry and wet phases of the MJO themselves have waves propagating back as Rossby waves and forward as Kelvin waves that can create perturbations to the next phase or the propagation eastward in terms of the subsidence, reorganization of SST, and so on. The idea by Wong and Shi is similar, that when there is a onset of convection, there is Kelvin waves, there are Kelvin waves and Rossby waves, and the Rossby waves would tilt and head back towards the subcontinent and provide you mesos. Why would they tilt this way? There are ideas, and we will see one of them, that actually when you consider the vertical shear that we have already talked about in terms of the easterly shear associated with the monsoon basic state, then that shear can interact with the waves to produce a kind of sequence of events that relate the vorticity and convection to create northward propagation. So there is some merit to this idea, even though the assumptions that go into it are debated in terms of whether that idea actually gives you propagation across the equator that we saw before, for example, originating in the marine ITCZ, going across the equator. The idea works if they are originating somewhere here in the northern hemisphere and not close to the equator, where F is small and beta is large. So there are some details in the assumptions involved there. We will see that in a minute, but other ideas suggest that meso is an internal mode which would require self-regulation and self-induction, which I already implied. So that's kind of the extension of the internal mode theory, where you either invoke interactive land hydrology. So if there is a previous active period which has created, let's say, enhanced soil moisture, then you get something like a land WISHI, the wind-induced surface heat exchange, which can provide you the kind of an attractor to pull the meso towards land. Of course, the problem is that meso is very active on the Bay of Bengal and then onto land, and not directly from the ocean onto land. So land hydrology in that sense doesn't directly cause mesos, but it's considered a factor that favors northward propagation. I'm being kind of very descriptive, but that's because these are just theories that have not been completely validated and explained fully. Okay, so going back to our relation between the heating and the vertical stability in the convection, which we related to the Brent-Vesala frequency as well, we can take that also related to the Mayu-Bayu frontal zone, which kind of starts as a stationary front and propagates. So those ideas of heating and propagation can be related this way to the land hydrology. So this is a schematic of the theories for northward propagation. Role of land surface hydrology, processes, hydrological processes in encouraging the northward propagation of the meso. That's not a very scientific terminology, but nonetheless, they create conditions which are favorable for northward propagation in terms of sensible heat exchange, latent heat exchange, and the moisture loading required ahead of the convection that starts in the deep tropics. Okay, heavy dashed line denotes land area. So we have land and ocean. So you have equator and northward direction here. Latitudinal profiles of typical mean daily meridional profile of circulation. Second one is surface temperature, groundwater content, surface albedo, which is important for radiation balance, surface evaporation, all the hydrological processes, vertical velocity profile W, total columnar heating are shown here. Note that total heating leads to vertical velocity, signifying a northward propagation. So you have an active period here, subsidence over the deep tropics and the equatorial region. So that is the circulation part. Surface temperature, when this happens, you have warmer temperatures here, cooling under the convection and warming ahead of it in this branch. Groundwater content, obviously ocean, but land has increased soil moisture. It's not exactly groundwater, but soil moisture. Surface albedo for the ocean is low. For the land, it can be low when there is wetness and high when there is dry soil. Evaporation is high on the ocean, and there is, of course, evaporation associated with the moisture convergence into the heating region of convection. So the total heating and vertical velocities end up showing this feature where the heating is ahead of the vertical motion, which favors, here is the tip of the Indian peninsula, and that shows the northward propagation. As I said, there is hardly ever direct propagation onto land. It usually is very strong over the Bay of Bengal. As I showed the animation in one of the podcasts, the ITCZ, the split, the northward propagations are all happening in the central eastern Indian Ocean, a little bit to the east of peninsular India, even though there is a branch that goes up the Arabian Sea and curves on to the peninsular India as well. So the surface hydrology propagation feedbacks is a different idea. This is that's the this figure. This is vertical shear and propagation. So this argues quite elegantly that there is basic state vertical shear, easterly shear. So you have upper level easterlies and lower level westerlies that are the basic monsoon circulation. You have convection north of the equator, which has vertical motion, and the vertical motion has drops off behind it and has a positive gradient ahead of it. And the vertical shear, you can curl your fingers and gives you a barotropic vorticity, but the vertical motion associated with the convection and the shear is so strong that it can tilt the barotropic vorticity, which combined with this vertical velocity can give you anticyclonic circulation behind and cyclonic circulation ahead. So it creates moisture loading and favorable condition for the convection to move northward, and then the convection and the vorticity end up getting created north of the original convection, giving you northward propagation. This is a nice work, but there are many debates about it. It's not completely agreed upon, but you can take the vorticity stretching term. Of course, we know that such a vertical shear would create wave modulation in the vertical and trapping and energy and all those good things that we need. But you can also look at the meridional gradient of the vertical velocity in the pressure coordinate with the vertical shear to look at this vorticity tilting that is shown here, and the vertical shear is strong enough that the tilting effect can be strong. So that gives you kind of a self-regulation, self-induction kind of process for MISOs. Okay, I kind of ran through these because these are ideas, as in the case of MJOs. When you have multiple theories, it just means that there are many open questions. Doesn't mean we have to rush through them, but anyway, we are not doing the detailed mathematics of it. Further detailed discussions are given in many review papers and in a book by Tim Lee and his colleague, I forgot the name, which is also on the tropical dynamics. So you can look up those books both for MJO and MISO dynamics, which are done in much more mathematical details. In the next chapter, actually, we will revisit some of the coupled dynamics of the monsoons as well. Okay, so I will leave it here.